Okay, welcome Math Counts friends. Welcome back to our Geometry Fun series. Today we are doing part 5 and it's going to be the shoelace theorem. So let's jump right into it. If you need to see the previous videos, I'll have links in the description. So what is the shoelace theorem? The shoelace theorem. That's an interesting name. Fun name. The shoelace theorem is a way to compute the area of any polygon if you know the coordinates of the vertices. So let's say you have a polygon that looks like this. And it's got vertices maybe here, 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 and here. And what you do is first you need the coordinates, right? So you've got x and y coordinates. This might be x1, y1. Okay, and then the next point, this might be, if we call this point 1, and we'll call this one point 2, 3, 4, 5, and 6. This would be x2, y2, as its ordered pair. This would be x3, y3, and this one would be x4, y4, and this one would be x5, y5, and so on. Of course, this one would be x6, y6. Okay, so say you're given all these coordinate points and they ask you the area. What you do is you write down all those coordinates in a pattern that looks like this. So you write the x1 value here and the y1 value right below it. Then you write x2 and y2. Then you write x3 and y3. And then you write x4 and y4. Then you write the x5 value here and the y5 value here. And the x6 value and the y6, and you might think we're done, but we're not. You have to take the first point and write it again, x1 and y1. So you write all those numbers down, and then you start multiplying. So you multiply in two different directions. First you multiply in this direction, diagonal to the right, down and to the right. You multiply those two, each of those pairs. All right, so this will give you, for example, x1 times y2. This will give you x2 times y3, and so on. And then you go and you multiply in the other direction, up and to the left. y1 times x2. And then you get y2 x3, and so on. And what you see if you continue to do this is that you form a pattern that looks like shoelaces, and that's where this theorem gets its name. The shoelace theorem is because it looks like you're stitching up your shoes with these little crosses here. Now, how do you get the area from all this? Well, what you do is you take all these products that you got from multiplying down and to the left and you add them all up. Okay, so this plus all the way up until you get some sum here, sum 1. And then you take these other products that you got, x1 or y1 x2 plus y2 x3 plus dot 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 all the way to the end, and that's going to give you another sum. This is sum 2. And then you can compute the area, A, as the absolute value of S1 minus S2 all divided by 2. So basically you just take the difference, the positive difference between these two sums, and you divide it by 2. And that'll give you the area. So that's all you need to know to be able to use the shoelace theorem. One thing I'll mention is that if you always, well, I guess I better mention a couple things. One thing is that you need to order the points in the counterclockwise direction, or in the clockwise direction, but you shouldn't jump around. Like you shouldn't go from here up to 3 and then down to 6. You shouldn't name this one 1 and then this one 2 and then this one 3, and you shouldn't jump around. You have to either go order in a loop one way or the other way. And if you always go counterclockwise, I think you don't need this absolute value. You can try it out, but I think if you always go counterclockwise, you just do S1 minus S2, and it'll be a positive number. Whereas if you go clockwise, it'll be a negative number. You can it's either that or it's the other way around. You can check it out and find out. But in any case, I don't like to have to remember whether I have to go clockwise or counterclockwise. So I just always say whatever. When I take this difference, I'm going to take the positive value. Because if I take the negative value and divide by 2, I'm going to get a negative number, which is not going to make sense for the area of this polygon. The area has to be positive. Another thing is that this is not going to work if the edges of the polygon cross each other. So like, and I guess that's kind of the same thing as saying you have to do it in a clockwise direction. Like if you were to take these 4 points here and you were to say there was a polygon that went like this, that's not really a polygon because you've got these 2 edges crossing each other. What you actually get when you do this is the difference of the area of those 2 triangles, which is kind of interesting also. But if you want the area, you need to order the points around the loop like this, and then the edges won't cross each other when you connect them up. All right, what else? I guess another thing I should point out is that the polygon does not have to be convex. You can see here that this polygon I used was not convex. So it can really be any polygon you want. And it works. Yeah, it just works. So let's go ahead and prove this one now. If you don't want to see the proof, feel free to stop here, but I think this proof is a lot of fun. So let's go ahead and do a proof of the Shoelace theorem. Okay, so I'm going to draw maybe a coordinate axis. So let's draw a vertical line for the y-axis. Let's draw a horizontal line for the x-axis. And let's maybe start with a simple case to get us started. And for this simple case, I'm going to say that we've got a triangle. Not any old polygon, but it has to be a triangle. And not only that, but I'm going to constrain my situation so that one of the points is at the origin. And the other 2 points can be wherever. So I've got this triangle. One of the points is at the origin, and the other 2 points are somewhere else, and that gives me this triangle here. So I've got my coordinates 0, 0, and my coordinate x, let's call this x1, y1, I guess. Or maybe I should call it x2, y2, since 0, 0 is my x1. So let's call this x2, y2. And then let's call this one x3, y3. So when we do our Shoelace theorem, what are we going to get? We're going to get 0, 0 here. We're going to get x1, y1 here. We're going to get x2, y2 here. And we're going to get 0, 0, because we have to duplicate the first point at the end. All right, so what are we going to get when we start multiplying this all together? Well, this first multiplication is going to be 0. This one is going to give us x1, y2, and this one is going to give us 0. So my sum is just x1, y2 for the down and to the right sum. Now if I move on to the up and to the left sum, I'm going to get, again, I'm going to get a 0 at the first one and a 0 for the last one. So you can see now why I picked one of my points to be at the origin. It made things pretty simple. And then I just have y1, x2. y1, x2. So if I compute the difference between these two, I'm going to have x1, y2 minus y1, x2 all divided by 2. That should give me the area of this triangle. Now, can we prove that this is true for this simple case? And then we'll use this simple case to prove it for a more complicated case. So how are we going to do this? Well, first thing we need to do is we need to draw a rectangle. Okay, so let's see, let's draw a rectangle, and it's going to start with one corner at the origin, and it's going to go as big as it needs to be so that it just fits my triangle. Okay, so just big enough to fit my triangle. Oops, I did not want to make a filled rectangle. Let's see if we can. Yeah, I'll just draw lines because that'll be, I didn't realize it was going to fill my rectangle. So let's just draw lines like this, and we'll do our rectangle that way. Well, that doesn't look very good. Boy, it really doesn't want to go straight the way I want it to, does it? Maybe it wants to snap onto that other line, and I made that other line too short. We'll fix that. Okay, so let me just draw it. This rectangle like this. Okay. So first of all, let's start with the area of that rectangle, and then we can subtract off these 3 triangles. And that should give us the area of the blue triangle. So what's the area of the rectangle? So let's call that AR for area of the rectangle. That is just going to be equal to this width, which is the difference between this x-coordinate, x2, and this x-coordinate, 0. So that's just x2. x2 is the width, and the height will be the difference between this y-coordinate, y3, and this y-coordinate, 0. So that's just y3. What did I do? Oh, I am sorry. I put x1 and x2 down here when this should have been x2 and x3. So these should have been 2's. My apologies. You guys have been screaming into your YouTube app telling me this, and I haven't heard it until now, but this will be x2, y3. This will be y2, x3. This will be x2, y3. This will be y2, x3. My apologies for that. Okay, so the area of our rectangle is x2, y3. Now let's look at the area of these triangles. So let's give them names. Let's give this triangle 1. Let's call this triangle 2. Let's call this triangle 3. And then maybe we'll call this one triangle 4, which is what we're going to try to compute. So we'll say A1, the area of this triangle. That's going to be base times height divided by 2. So that's x3 times y3. So this is x3, y3 divided by 2. And the area of triangle 2 is going to be x2, y2 divided by 2. So this is x2, y2 divided by 2. And the area of triangle 3 is a little bit more complicated. This distance here is x2 minus x3. So let's do A3. x2 minus x3. That's the base, and then we have to multiply by y3 minus x2. I'm not going to have enough space there, so let me just clear this out. We'll write it over here. A3 is equal to x2 minus x3 times y3 minus y2. y3 minus y2 all over 2, right? So this is x, let's draw it in yellow here. This is x3 minus x2 is this distance, or sorry, x2 minus x3 is that distance. y3 minus y2 is this distance. So those are the base and the height times, and then divide by 2. That will give us that area. So our final area is going to be the rectangle area minus this, minus this, minus this. So let's make some room. See if we can figure this out down here. Let's see if we can figure this out. Oh boy. Alright, so our final area is going to be equal to AR minus A1 minus A2 minus A3. And that is going to be equal to what? So looks like I've got a lot of things divided by 2, so maybe I'll make AR 2x2 y3 all divided by 2. Well, at the end I'm going to divide everything by 2, so this whole thing is going to be divided by 2. So I need to subtract A1, which was x3 y3 divided by 2, x3 y3, and then the divide by 2 is here. And then A2 is y2 x2, or sorry, x2 y2. And yeah, I'm running out of room here, but it's this product here. So maybe I will put another, I will just kind of arrow it up to here. My apologies, but this is going to be, we're subtracting a3, so we have to subtract x2, y3. So minus x2, y3. And we're going to do FOIL. So that's the first. The outside is x2, y2. So minus x2, y2. And I'm going to make another row. So actually, let's see, did I do that right? This is actually a plus because I'm subtracting a negative. And then if I do the inside, it's also a negative. So that'll be a plus x3, y3. And then this is going to be a negative times a negative, but we're subtracting it, so it's going to be a negative x3, y2. Hopefully I can cancel some stuff out here. So what have I got? So I've got a positive x3, y3 and a negative x3, y3. Those two can cancel out. I've got a negative x2, y2 and a positive x2, y2. Those two can cancel out. And then I've got an x2, y3 here and a negative x2, y3 here. So this can cancel out with one of these two. And then now I think that's all I can do to simplify things. So let's take a look at what's left. I've got this x2, y3, and I've got a negative x3, y2. And that is all divided by 2 here. So is that the same thing? Yes, it is. It's the same thing we had up here. Okay, so we've proved the Shoelace theorem for a triangle where one point is at the origin. And now comes the fun part. Because every polygon can be broken down into triangles. And yeah, we're going to see how this works. So let's do some things here. So actually I want to point out first of all that if you were to swap which one is 2 and which one is 3, then you plug those in here, you would get, I'm going to call that A prime. If you swap the 2 points, you get A prime. What is that? Well, that'll be equal to x3 y2 minus y3 x2. Just change all the 2's to 3's and all the 3's to 2's, and that's divided by 2. And what is that? Well, look, it's actually exactly the opposite of A, because this minus y2 x3 is positive over here, and this positive x2 y3 is negative over here. So we've really got A prime is the negative. So what happens is, if you order your vertices in the other direction, you get the negative, you get the opposite area. So you'll get a negative area if you put the second point further clockwise than, further counterclockwise than the third point. So here we had the second point was the more clockwise one, and the third point was further counterclockwise. Does that make sense? If this is like, by clockwise I mean if you had like a minute hand here, right? If this is a minute hand and this is an hour hand, you know, here the minute hand is further clockwise. So that's point 2 is further clockwise and point 3 is further counterclockwise. Then you get, if you have this, then you get a positive area. And if you do the other way around, where the second one is further counterclockwise and the third one is further clockwise, by swapping the 2 points, then you're going to get a negative area. So that's an important thing that we're going to need to know when we start putting these triangles together. Okay, I'm going to make some room. Well, why don't I just erase all of this and we'll start over. All right, so we have proved the Shoelace theorem for a very specific case. And that case is where they have a triangle, and that triangle has one of its points at the origin. All right, so let's see what happens now if we have some other quadrilateral. Okay, so maybe let's say I have a quadrilateral that looks like, or not a quadrilateral, a polygon. Well, we can make it any number of sides that we want. It doesn't have to be 4. let's say we have a polygon that looks like this. That looks like one side, doesn't it? Oh well, that can be one side, that's fine. Okay, so now maybe I'll draw my axes as well. So let's draw a y-axis, something like that. Should probably do it in a different color. Oops. Oh, that's not what I wanted. There's my y-axis. Here's my x-axis. Something like that. Okay. Now, what I can do is I can break this polygon down into a bunch of triangles, and each triangle will have one of its points at the origin. Okay? So I think hopefully you already see where I'm going with this. I'm just going to draw these lines from the origin out to all the vertices. Oops, that's not a very straight line, but out to all the vertices of the polygon. And now I can do the shoelace theorem on each of these individual triangles, right? So if I were to do that, let's just say this is triangle 1, 2, 3, 4, and 5. And let's say that this is my x1, y1, and this is my x2, y2, and so on. This is x3, y3. Let's see what happens when I start doing the shoelace theorem on these triangles. Well, we know that, well, I mean, I guess it's pretty simple just by looking at the construction, that if we do the shoelace theorem on each of these triangles and we add up the areas, that should give us the area of this pentagon. But let's see what happens when we write that all out. So we'll have, for the first triangle, we'll have 0, 0, x1, y1, x2, y2, 0, 0. Okay? And then for the next triangle, we'll have 0, 0, x2, y2, x3, y3, and 0, 0. And so on. And if you compute each of these shoelaces, you know, you do the shoelace here, and the shoelace here, and the shoelace here, what you'll find is you'll get x1, y2, x1, y2, minus y1, x1, all divided by 2. And over here, you'll get the same thing, but with 2 and 3 instead of 1 and 2, right? So that'll be, I didn't leave myself much room, maybe I'll write it over here, x2, y3, minus x3, y2, all divided by 2. And I guess what I should do is show you that that is the same thing that you get when you do the shoelace theorem on the quadrilateral that is formed by putting those two triangles together. So if you were to put those two triangles together, you would get this quadrilateral that covers all this area in 1 and 2. And if you were to do the shoelace theorem on that, you'd start at 0, 0, 0, 0, and then you'd have x1, y1, x1, y1, and then you'd have x2, y2 right away without having the 0, 0 in between. X2, y2. Oh, I should say that's the same as this. But now, instead of going back to 0, 0, we go over here. We do x3, y3 directly, and then back to 0, 0. And if you do the shoelace theorem here, here, and here, you're going to get this plus this. And you can just carry on with that. Add another triangle. You'll add another one of these. And it's just like adding on the x4, y4. And yeah, eventually, you know, once you add, and then you add another one, and now you've got, once you add the second to last one, I guess your shape is now going to be this weird shape that goes around. Oops, I didn't draw that very well, but you get the idea. It goes around like this. We're just missing the fifth triangle, but it still goes back to 0, 0. And then you just remove 0, 0, and it'll bing, connect back here, and you'll get the full shoelace theorem. So it works out great here. But you might be looking at this and saying, hey, this doesn't really work if the origin is not inside the polygon. What if the polygon is all out here? You're not going to be able to make these 5 triangles because the origin is not there. So let's take a look at what happens in that case. It's actually not that different, but it's kind of cool to see what happens. So let's take a look. We'll erase everything again. Maybe I should have drawn my origin, my coordinate system on a different layer so it wouldn't get erased, but anyway, it is what it is. Alright, let's draw my coordinate system again. Oops. Okay, I'll put vertical axis, horizontal. Actually, why don't I put it over here so the origin will be down here so I can have my polygon kind of as the focus away from the origin. So here we go, there's an x-axis. And now, let's say my polygon is here. Let's grab blue, I guess. So let's say my polygon is here. Okay, so I've got these 5 points. Now what happens if I do my 5 triangles? I can't do the 5 triangles into this point here where they're all going clockwise. What's going to happen is I'm going to have these triangles like this. There's going to be one here. Oops. And maybe I'll just use this straight line tool. I should do these in different colors too. Okay, so I've got lines going, whoops. Line going here. Got a line going here. Got a line going here. A line going here. And a line going out to here. It's hard to see that one. Maybe I should have moved this point out a little, but it's okay. We'll have a triangle with 0 area there. That'll be fine. Okay. Actually, it might kind of be nice to have that. All right, let's take a look at what happens. So let's call this triangle with, let's name the edges, so that'll help us keep track of the triangles. So let's name this edge 1, this edge 2, this edge 3, this edge 4, and this edge 5. And then you can get the triangle corresponding to edge 1 by just, starting at the origin and going out to those 2 points, basically. So that's triangle 1 here. And what I want you to remember is that, if we name these, maybe I should, maybe I'll give letters for the triangles and numbers for the points. Let's do that. Let's call this vertice number 1, 2, 3, 4, 5. That way we can have point 1 through 5. And then we can call this A, B, C, D, E for the edges. Okay, so triangle A, the one from the origin out to edge A, that one has this area here. And if we do the shoelace theorem on that, we'll get that area. Okay, and then triangle 2, same thing. We get this area here. And then I'm sorry, I shouldn't have called it triangle 2. This is triangle A, this is triangle B. Now we do triangle C, and that gives us this area here. And we've added up all those areas, and we've already got an area that's bigger than our polygon. But some interesting things are about to happen. So first of all, triangle D. I guess since this triangle either has a very tiny area or it's a 0 area if these are really on the same line. Let's just say they're on the same line. This is going to give us 0. And actually, that's kind of interesting. Let's write that out. When we do the shoelace theorem on this, we're going to get x4 y5 minus x5 y4 all divided by 2. But what's interesting is that because these points are on the same line from the origin, x4 is just some ratio bigger than x5, right? So like, for example, let's say that this distance out to number 4 is, I don't know, looks like it's about let's say 70% longer than the distance to 5. So that means that x4 would be equal to 1.7 times x5. And at the same time, y4 would also be equal to 1.7 times y5. Okay? And if we plug those in here, I mean, the 1.7 doesn't matter. It's some constant multiplied by the other. But if we plug those in here, well, something interesting happens. So we get x4 times y5, which is I guess, yeah, well, let's just say y5 here, and then minus x5. x5 is x4 divided by 1.7. Let's do that. x4 divided by 1.7. And then y4. y4 is 1.7 times y5. So this is times 1.7 times y5. And what happens is the 1.7's cancel out, and you get x4, x5 minus x4, x5. That's just 0. You get 0 over 2 is still 0. So yeah, that triangle is going to have area 0 if they're on the same line from the origin like that. So that's kind of cool. All right. So we've still got this area that's too big, right? Because we added up these 3 triangles, and then we added in this area of 0. And so we've got an area that's too big. It's bigger than the polygon. But now, look what happens. When we do this final triangle, it's with 0.5 and 0.1. All of a sudden, now 0.5 is the one that's further clockwise, and 0.1 is the one that's further counterclockwise. So, you know, we were going in this order around. As we went in this order around, when we did this triangle, as we looped through the vertices in this order, it was the second one that was further counterclockwise. You know, in other words, out of these two, the second one was further counterclockwise. Out of these two, the second one was also further counterclockwise. Out of these two, the second one was also further counterclockwise. These two are both the same because they're like the hour and the minute hand are pointing in the same direction. So neither one is further clockwise or counterclockwise. That's why you get an area of 0. And then here on this last one, the second one is further clockwise. So we're going to get a negative area. And so what's going to happen with this negative area is this, this area here is going to get subtracted off. And that's going to get us back to just the area of our polygon. So really cool how that works. You know, the Shoelace theorem will work regardless of whether the polygon is surrounding the origin or not. You just plug and chug, and you can figure out the area of any polygon from its coordinates. So I hope you guys really enjoyed that. I think that's kind of a cool proof, and I will see you guys in the final video.